was done by a couple of my students, Min Jan and Declan Russell, talking about applications of SPH in sampling, and also so how you do it, and also what it can be applied to in problems in computer graphics. So to take a method from computer graphics and then to use it to come full circle and apply it to new applications. So you may be familiar with basic sampling theory. If we have a signal, such as it's demonstrated in the top image, the principle of the Nyquist limit is that we should sample a signal at 2 times the frequency of the signal so that we pick up all the salient features in the signal. If you sample at a frequency, if your sampling density is lower than twice your frequency, you're going to end up with artifacts like you see in the bottom image. So that's a sort of a basic principle about sampling, and that makes sense in 2 dimensions, but in 3 dimensions it's not quite so straightforward. Or sorry, that was a 1-dimensional signal, but in 2 dimensions it's not so straightforward. Here's an example of various methods for half-toning. And the method of error diffusion is a method where it tries to position the dots with a density function such that they're equally probable to be equidistant from each other, subject to the probability density function. And that's the figure on the far right, which gives the best error diffusion results in comparison with functions which use either white noise or regular grids for the half-toning. And this is a technology that's used in printers today. I think the other thing obviously to say is that it means that we use less ink in our printers by using dots. So one of the things that we know about human vision is that we all have a tendency to see patterns in things, and it's a phenomenon called apophenia. It is a distracting phenomenon in half-toning, as you could have seen in the previous image, where we had, in the adaptive tessellation, you could see these patterns forming, and that can be a distraction. And of course, we can see it in a slice of toasted cheese bread, which was, this particular lovely example was sold on eBay for, I think, $25,000. Because apparently you can see I think it's the Virgin Mary, I'm not sure, maybe it was Jesus, in this toasted sandwich, which is debatable. In rendering, however, sampling is super important when it comes to things like strobing, jaggies, and moiré patterns, which occur in a common phenomenon that occur in rendering when your sampling is not chosen correctly, or at least you use possibly regular patterns for choosing your samples. And in simulation, it's a problem which we have in particle-based simulations where we might have a boundary. So if we have a boundary between 2 different types of fluid, or a fluid and a surface, the regularity or the sampling of the boundary particles can really affect the nature of the interaction, and I do have some examples of that later. So these are 2 examples of noise generated with the method that I'm going to describe. The one on the left is a noise pattern distribution that actually it does qualify as blue noise, but you can see very easily there is patterns forming. So there are sort of regular chunks of points where you can see that there are 6 neighbors to each individual point. And then there are boundaries between these regular chunks, which your eye can kind of pick out when you look at it, the image on the left. And the image on the right, you can't really see these patterns forming, although you can see almost circular sweeps in the patterns. Maybe I've just been staring at these images for too long. So this is the principle of apophenia, and even within blue noise distributions, you can see the difference between, qualitatively, the difference between these. And these we can effectively quantify by using various tools. So this is a form of Fourier analysis, which allows us to investigate the frequency distribution or spectral patterns of a particular distribution. So the image on the left sorry, the examples on the left, we can see that we have lots and lots of ripples here. So what you see in this image here is it's essentially if I took a slice from the center out to the edge. So these peaks here are corresponding to the white rings. So as we go from the center out to the edge, we can achieve these, it'll achieve this sort of pattern, which may not be the type of pattern you want. Certainly all of these spikes imply that there are irregularities there. And this pattern here is the pattern going around the circle, if you like. So if I follow the pattern around the circle, so if I took these two functions, if I integrated this one, if I integrated this one by this one and did a sweep around, I would essentially end up with this final figure. And on this figure on the right, you can see that the distribution is quite different. The peaks are smoothed over, they don't have quite such a high amplitude, and the pattern on the right here is much more regular. So this gives you an idea of two different types of flavors of noise. Obviously the one on the right might look more visually pleasing, but both of them will have applications in graphics. So blue noise itself is we use color to describe different types of noise. So there's pink noise, brown noise. I'm not going to go into all of the detail of all of these, but the definition of blue noise is the inverse frequency power spectrum distribution. And the example on the right is of Cherenkov radiation, which actually does exhibit a blue color due to the refractive index as a result of the distribution of the Cherenkov radiation. Don't ask me to try and explain that, but there's plenty of information out there online if you want to know more detail about that. The minimal low frequency components means there's fewer spikes of energy, but most importantly, there needs to be an even distribution of these spikes. So we don't want any clumps of particles, and we need a nice even distribution. Now, I just mentioned Cherenkov radiation, but these also occur in all sorts of other types of areas, such as in cell growth, so in retinal cells, so cells in your eye. They also exhibit good blue noise properties in terms of the distribution of cells, and also occurs naturally in music. So there are lots of ways of generating blue noise. This is certainly not the first method I'm going to present today. Poisson disk sampling is one of the earliest and most effective methods of generating blue noise. The algorithm I can explain in a second, I think. It's just you throw a dart at a dartboard, and if it's too close to another dart, you discard it. And if it's not too close to another dart, you keep it. And you keep doing this until you've discarded quite a few in a row. And then what you do is you shrink your radius of closeness. And that's the algorithm for Poisson disk noise generation. There are also other methods involving Voronoi tessellation, Wang tiling, or other types of tiling methods. And there are other methods as well that use physics or use physically based approaches, such as n-body simulation. So there are countless ways of generating these types of noise profiles, and all of them have pros and cons. So I'm going to talk a bit about Smoothed Particle Hydrodynamics, because I think it's important to understand the method that we're going to describe. So SPH, or Smoothed Particle Hydrodynamics, is widely used in graphics and other areas as well. It's a useful method because it's particle-based, it's mesh-free, so we don't have to do any meshing. Although obviously we do need to know something about the neighborhood if we're going to implement this efficiently. But it is able to capture quite a wide range of powerful effects, as you can see in some of these images. And there is certainly a devoted community that works very closely with SPH and applies them to very practical applications in engineering. But as you can see, it also is capable of capturing viscosity, collisions, vorticity, and of course very large-scale wave breaks. So it was originally developed for astrophysical problems, so problems in planetary motion and star formation. But it turns out it also had applications in graphics and engineering. So as I said already, that it's mesh-free, so the deformation is defined by free particles which basically influence each other based on how close they are. And one thing that's really interesting about smooth particle hydrodynamics is that it naturally encapsulates a process which diffuses momentum. So what that means is, without any external factors, if I ran a SPH simulation, after some time it will converge to a steady state, because what's happened is the momentum has been diffused evenly throughout the fluid container, between all the particles within the fluid container, until it's essentially a steady state. And that diffusion of momentum is essentially the property that we exploit in order to achieve a sampling. Okay, so this is called the Navier-Stokes Equation. It is a very well-known equation. It's if you can solve it, I don't think it's been solved yet. I stand to be corrected. If you can solve it, you can get $1 million. There are some terms here which are important. So rho is the density of the fluid, P is the pressure, mu is a constant for viscosity, and this is the viscosity term here. And then, of course, we have gravity. So typically what we do is divide through by the density to get a form that is integrable. But it's actually not that sophisticated if you think about this as essentially being force equals mass times acceleration. So this here is the force, and if you decode these terms here, you'll find that it's essentially, sorry, this is the acceleration, and if you decode these terms, you'll find out that this is essentially the force over the mass. So the system itself is actually not that easy to solve, certainly not outright. Typically we would use iterative methods to solve this, and the iterative process of solving this is how we basically create fluid simulations, or stock market projections, or whatever else people are applying the Navier-Stokes equation to. Most methods will break this equation up and solve each term separately, which is no different in the SPH solver. So the first one here, which is probably the most important term, as in terms of the amount of influence that this term will have on the amount of influence that this term will have on the whole equation, the pressure gradient is the most important. So when we talk about advection, we're talking about the flow, but pressure gradient, I know it's rather a disgusting metaphor, but it could be thought of as squeezing a pimple, because what we're doing is we're applying pressure from all different sides, and then the result is that hopefully, volcanic eruptions. So that's how one might define the pressure gradient. So it's effectively the resultant vector from applications of force from the various surrounding areas, and that defines how the fluid is going to flow. One of the principles that's applied throughout in SPH is this formulation, which is that of a function f of s and t, so s being a position and t being a time, we can define it in terms of the local region and functions and functional values at known fixed points x, and this allows us to essentially interpolate properties in a spatial field. So let's say we've got all these little blue particles sitting around here, and they all have some value associated with them. So if I have a particle at a fixed point, I'm going to call that point x, right? Because that's a known position. And f of x at a particular time t is the value of some function defined on those points. So let's say one of those values is density. So let's say we've got every one of these little particles has some density. So therefore f of xt, if this was my point x, would be the density of that point. Okay. W, s minus x, so x is the center of my kernel function, and w is my kernel function. So this is just a weighting function, nice smooth weighting function defined over my domain. And s is going to be the center of my domain, the query point, the red point there. So what this means is I can use this formulation here and this kernel function multiplied by all the values of known points around the space to get me the value at f of st. Okay, so this is a fairly straightforward bit of integration based on a kernel function. what we do first is we discretize this principle by saying, okay, well, what we want to do is we want to evaluate the integration, but at the sites of the particles. So what we want to do is we want to evaluate the function at each particle based on the function value at all the neighboring particles. So we're going to discretize that integral into a sum. And then what we end up with is this term here for the integration, which is the volume associated with each particle. So that's that delta Vj is the volume. So now what we're doing is we're essentially performing numerical integration using these properties stored at the particles, such as, for example, density. So, and essentially we're just doing a Riemann sum, or at least a weighted Riemann sum. Okay, so the volume term here, we can basically use the principle that mass times volume is density, and then essentially replace the volume term, this one here, with mass over density, which basically gives you the general form of the SPH weighted numerical integration. So here we're going to apply it to a very straightforward example, which is the calculation of the density of the local particle. So for the density, we have rest density, which we're going to apply, which is rho 0. So the rest density of water is about 1,000 kilograms per meter cubed, I believe. For the density term, what we want to do is we want to evaluate the density at a particular particle. So what we're going to do is we're just going to take the current density, which is going to be F rho at the current sites, and we'll replace it into our interpolation function. And it's very straightforward, so because these two terms cancel, and we end up with just the mass times by the weighting function to evaluate the new density term. So once we've got the density term, we can evaluate the pressure, and the pressure, of course, in this case, I'm using the very simplified equations of state, which are based on pure gas, but there are numerous ways of evaluating the equations, evaluating the pressure from the density. This one just happens to be the simplest and easiest to implement in your favorite parallel programming language. So once you've got the density, you can evaluate the pressure gradient. The pressure gradient, there are several different ways of evaluating the pressure gradient. So this is a symmetrical pressure gradient calculation. Not all of them are symmetrical. And essentially, as I said, it's the resultant force from applying the forces from all the different directions, which are essentially determined through the density and the pressure of each particle. And remember, the pressure is a vector. So this is commonly written in the form below, but you can see it's a very simpler. It's also very similar to the previous formulation, except for the grad here. So this grad symbol means that we're using the gradient of the weighting function, which is a different function, and quite often we may replace that function with a different function due to the properties. But I'm not going to go into that detail. So that was just to solve for the pressure gradient, which is one of the most important terms in an SPH formulation. But there are similar processes to solve for viscosity or other parameters. Now, the solutions often, to get useful solutions in SPH, you need to use lots of particles. So in that example there, which I'll play again, this was, I think it says it there, over 1 billion particles were used in this implementation. And that's running on 64 different GPUs. So essentially what we typically do is we'll use lots of particles, we'll figure out where they live in space to make our problem tractable. And the reason why is, just like all graphics algorithms, if we have some sort of spatial function that tails off as things get further away, there's no point in storing all of the particles in memory when we're evaluating something distant, far away, right? So what we might put it into some sort of grid-based structure. Then we would solve density and pressure for each particle. We'd evaluate all the forces, which includes the pressure gradient, but also viscosity, surface tension, maybe the interactions between multiple fluids. And then we'll update the particle positions through integration. Okay. So that was a very brief introduction to smooth particle hydrodynamics. Let's talk about how we can use it in sampling. So as a sort of a naive first step, we'd basically just turn off gravity. We'll crank up the viscosity because we don't want it to move too quickly. One of the problems with SPH is it can be very unstable, so we'll try and crank up the viscosity to stabilize it a bit, so it's a bit more like wading through molasses. We're going to just apply the standard process of SPH, which is to diffuse the momentum. And we obviously have to do something clever at the boundary. So the boundary sampling itself behaves differently to the rest of the simulation. And then we can evaluate, and then we'll end up with something maybe that looks a bit like this. And you can see the density of each particle is being visualized. So it starts off with clumps of red particles, but as the simulation progresses, they diffuse the density until they're evenly scattered, and you actually get a pretty reasonable distribution of particles. But obviously, there's a bit more to it than that. So these SPH simulations are producing particles that equalize density and pressure. But the question, of course, is this actually useful? So in the work that we did, we considered how we would interpret the convergence criteria of SPH in a sampling context, and so I'll derive that bit here. So the pressure gradient, which I've defined earlier, is this, and if we just use the pressure defined by the Tate equations of state for ideal gas, it's just those, but as I said, there are other equations as well. So a couple of things happen when SPH converges. Firstly, we would expect the difference between the particle positions in different time steps, which is demonstrated with xi plus 1 and xi. We'd expect the distance between particles to basically be quite small. So we'd expect each iteration not to move the particles much. So I think that's a sort of a fair assumption for convergence. Another thing which we would expect is that the density of each particle will start to converge towards the same. So not necessarily the rest density, because they might be under pressure, but we would expect the density of the particles all to even out. And then the other one is that the the pressure gradient is also going to become zero. So once the pressure gradient becomes zero, we would expect no particle movement. So these things all would be ideally starting to happen when our simulation converges. So as a mass, so if we assume our mass is zero, so we just wanted to get rid of the term, we can basically say, sorry, not the mass is zero, sorry. Assuming the mass is the same for each particle, which is just m, we can write it, we can essentially write this formulation, which is the convergence of the pressure gradient, to say that it's this term here is also tending to zero. And for that to be kind of meaningful, right, that would imply that one of these two terms is going to be zero, which is the gradient of the kernel is zero, or that the pressure is the pressure gradient, so this term would be zero. Sorry, not pressure, that's the density, would be the same as the rest density. So if we've achieved one of these two things, then we can assume that's what's causing the pressure gradient to end up being zero. Okay, so this gives us something interesting to work with, because we can manipulate the convergence of the SPH simulation by either making the kernel tend to zero, or we can manipulate the pressure, the density to tend towards the rest density. And so how we do that is we manipulate the rest density between time steps. And by doing so, we can actually get different types of blue noise distributions. And not just different types of blue noise distributions, we can get all of the different blue noise distributions in between by controlling these convergence parameters. And that's really the advantage of using this SPH technique, because you can basically produce a family of blue noise distributions. So here's an example of manipulating this convergence. So I just basically create some sort of parameter, lambda, and lambda is going to be a user-defined density difference, right? So the density difference is something that we're going to use as a method to control the rate of convergence. I can also manipulate it so that it takes longer to converge, or it converges quicker, but in general that will mean that the result would be not quite as a smooth spectral distribution. So, and then what we're going to do is, once we created this density difference, we reset or change, modify the rest density in each time step. If I just set row 0 to row I in each time step, the convergence will be far too quick. So what we have to do is we will come up with some way. I should say that again. If lambda was 0, the convergence would be very quick. So what we want to do is potentially slow this down so that we can get a more interesting rest density. So this is a family of different results with different values of lambda. So you can see that we can generate this sort of family of results from something that looks completely flat to something which has this number 25, which actually has one of the most desirable properties for a blue noise distribution, all the way to something that looks rather Voronoi in its nature, where lambda is very high. So this is quite powerful because this means that we can completely control the different types of new blue noise distribution. And in comparison with some other methods here, what we typically would do is we would plot the effective Nyquist frequency against the oscillation. So those were the spectral properties we had previously. Now there's normally a trade-off between these two properties. You can't really get perfect performance on both of them at the same time. And what we can show is that the SPH solution kind of fits neatly between previously published results. So that's a nice thing to have because it means we can generate blue noise profiles from anywhere in between this family. So there is plenty of other things to talk about, which I'm not going to talk about here, such as how do we do the surface tension and surface relaxation, which is really important to have a good distribution around the surface. And also there's details about how this can be implemented in CUDA. So let's talk a bit about applications. So one of the first applications was to use geodesic distance and essentially run a smooth particle hydrodynamic simulation on the surface of a piece of geometry. So you can see there in the bunny, we start out with a random distribution and very quickly, well, relatively quickly, it converges. I think that is slowed down so you could see it. And why you might want to do this is you might want to do a nice high quality remeshing. And one of the things that we do see with this type of method is that it naturally, because of the way that the surface properties are calculated in SPH, it does naturally adhere to the corners or edges of the geometry. So this has actually some really nice properties for surface remeshing, and we demonstrate in the paper that in comparison to other methods, this is actually quite an attractive method for remeshing of surfaces. So another useful thing is that we can create a spatial function. So we can create a function of space that essentially manipulates the distance between particles. So what we're doing is we're basically messing around with the kernels by coming up with some sort of size function that allows us to adaptively change the distance between the particles, or the rest distance between the particles. So that's how this example here gets resampled, so that the regions so that starting with a random distribution, it will essentially converge towards the regions of higher desired density. And that's really useful when you have full volumes like this bunny here, where we can basically say, if we want to do a tetrahedral meshing of this bunny, for example, we can use this adaptive sampling to give us sparse tetrahedra in the interior regions of the bunny. Of course, there are many methods to do this, so we didn't compare them. However, this isn't ideal, and I'll have a slide in a second. There is a unique property about SPH, which is its ability to demonstrate multi-class noise. So using some straightforward geometric functions, which we do in the paper, it's possible to have a distribution where we have different classes of noise. So in this case, red dots and blue dots, where the combination of these dots is also blue noise. So the example, the samples on the left are blue noise distributed, but each of the individual subclasses are also blue noise distributions. So this is possible with any number of classes, but I should just warn you that if I had red, green, and blue, any combination of two classes will not be a blue noise distribution. It would have to be all of the different classes combined would be a blue noise distribution, and each one of the separate classes would be blue noise distribution. I think it would be impossible to come up with a method where subclasses would also be random combinations of subclasses would also be blue noise distribution. But I think the most compelling result of all of this was just to think about how the blue noise distribution actually impacts on SPH itself. So this was a little experiment to just take a sphere, pack it with lovely blue noise sampled particles. And the figure on the top was just a sort of a naive packing, a grid packing, which is actually a method that is currently used in SPH for solids. And the one down the bottom was using the SPH method for blue noise sampling. And then what we did was we just took a query site, which is just a blue point, and we moved it around the surface of the circle. And with uniform sampling, you can see that the density is actually all over the place. In fact, it ranges between variously from, say, above 5,000 to 3,000, whatever this is actually. I don't know what the units are. So the density function varies wildly, whereas with SPH sampling, the density function is more or less smooth and certainly doesn't vary that wildly. And what you can expect from this result is that if you were to do surface sampling and you used SPH sampling for your surfaces, you should expect the SPH behavior to be more stable around surfaces, because these wildly varying density readings will cause your simulation to potentially be unstable. So I think this is something really important, and it's a very exciting result, and certainly applicable in a variety of different applications, not just on particle samplings of geometry for SPH simulations. So the properties of SPH sampling include the trade-off between these different noise profiles. So I think that's the main advantage of using SPH sampling, is that you are able to generate these different types of noise profiles within the blue noise spectrum. It is possible to do adaptive sampling. There are many published methods that do this as well. It is possible to do various applications, including surface and volumetric sampling, which is really helpful. And multi-class is actually quite a unique property of this method. However, the caveats to this is that blue noise is notoriously difficult. SPH is notoriously difficult to implement effectively. It typically would require GPU hardware to do so. And with very large sizes of points, it can be very expensive to do so, especially when considering other comparable methods like Wang tiles. Actually, one other disadvantage here is that with some of the other methods, they allow sort of zooming into the noise forever. That's not possible with SPH, because the particles you have are the particles you have. And I think it's also comparatively slow. So again, in comparison with tiling techniques, which are super fast, this sort of approach would be a bit slower. I just want to say a few other things from the paper, which we didn't really investigate too much, was the interesting phenomenon of what happens when we play around with the kernel functions. So we didn't really explore this very much, but we were able to create some interesting results in terms of different noise distributions from different kernel functions used in the Smooth Particle Hydrodynamic paper. So I do think this is an area for future work. So if anyone's interested in this sort of thing, please do get in touch. And this is potentially a problem as well, which I didn't really flag up in the talk. So one of the problems with SPH is that it doesn't really behave well in very sparse regions. So one of the things is that the pressure gradient becomes unstable if it has no particles in its neighborhood. So the figure down at the bottom shows the behavior around very sparsely populated regions, and you can see it sort of converges towards a tip, whereas some of the other methods would have an even distribution all the way out to the end when the density function is very small, evaluates to very low density. So it is very difficult to deal with extremely sparse regions with SPH sampling. So that is another concern. So that's it. Thanks very much. Get in touch if you have questions. And thanks to Ming Yang and Declan for their help with this. All right. Thank you. Cheers.